Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam. So today we're going to be working on the question on the screen that says calculate the change in entropy of a gas when 15 grams of CO2 gas are allowed to expand, or gas molecules, sorry, are allowed to expand isothermally from 1.0 dm cube to 3.0 dm cube at 300 Kelvin. So the first thing you have to do is to write out the parameters. We're told the mass of CO2 gas is 15 grams, right? We're also told that this is an isothermal expansion, so the change in temperature is zero, or the temperature is constant throughout the entire process. And we're also told that we have an expansion, so the V initial is 1.00, sorry, just 1.0 dm cubed. Okay, and then the V final is 3.0 dm cubed, and the temperature is 300 kelvins. So this is a very, very important question. Let me just rewrite the 1.0 again. 1.0 dm cubed. One thing you have to know is that when you have a question like this, where you're told that that is an expansion that occurs isothermally or an isothermal expansion, and you're dealing with entropy, well, it's important for you to know the formula, that the formula for the change in entropy in an isothermal expansion process is nR ln V final divided by V initial. So this is basically, this is it. This is how it's done. So when you have this information, you can now go on to solve the question. Note that in our situation here, we're told number of moles, right? We don't have number of moles, but what we have is mass as well as identity of the gas. So the number of moles is going to be the mass divided by the molar mass. So the mass of CO2 divided by the molar mass of CO2. So the number of moles is now going to be, the mass is 15 grams. The molar mass of CO2 is simply 44.01 gram per mole. So the next thing, of course, you do is for you to 15 divided by 44.01 gram per mole. That will mean the number of moles is going to simply be 0.34091 mole. So that's basically how you do with this question. So you have the number of moles, you have R, and you have the V final divided by V initial. So you can just simply substitute to the equation you have. So you have the change in S, the change in entropy is going to be 0.34091 mole, okay, times the gas constant, which is 8.3145 joule per mole Kelvin, times ln V final divided by V initial. So 3.0 dm cubed, okay, divided by V final, V initial. So that's just going to simply be divided by 1.0 dm cubed. Of course, you cancel out dm cube, 3 divided by 1 is 3 for, so it's ln 3. So you have mole here as well and mole as well. So you have the change in a second. So you have the change in entropy is just going to be 0.34091 times 8.3145 joule per Kelvin times ln of 3. So of course you input all of this information in your calculator to get the change in entropy to be 3.114 joule per Kelvin. Now, I want to quickly mention something, that this is the answer to our question. But because in chemistry, we would use the number of significant figures that is the lowest from the information given in the question. We see that 2 fig sig figs is the lowest. So we have to answer this question in 2 sig figs. So the final answer is just going to be 3.1 joule per Kelvin. So the change in entropy is 3.1 joule per Kelvin. So that is basically the answer to this question, 3.1 joule per Kelvin. So if you have any questions, please put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, estimate the change in molar entropy of N2 gas when the temperature is lowered from 298 kelvins to 273 kelvins, given that the molar heat capacity of at constant pressure of N2 gas or nitrogen gas is 29.125 joule per mole Kelvin at 298 kelvins. Now we're dealing with a change in molar entropy question, meaning that we're not trying to solve for the molar entropy for anything. We're just trying to solve for a change. So the first thing you have to do when you have a question like this is to write out the parameters. We're told that the temperature is lowered from, so we have the T initial to be 298 kelvins, okay? We have the T final is to be equal to 73 kelvins. So given that the molar heat capacity at constant pressure of nitrogen gas, that is Cp, comma m of N2 gas, is 29.125 joule per mole Kelvin. So we're told to estimate the change. So the first thing you have to note is that you've been given all of the parameters. Now we have to use our understanding of entropy in physical chemistry to write out the formula we're supposed to use. So we know the formula is the entropy at final temperature, or the molar entropy at final temperature is equal to the molar entropy at the initial temperature plus the molar heat capacity at constant pressure of N2. Okay, so I'm like rewriting it for this particular question. Actually, let me just ignore plus N2. I'm just going to give you the general formula and then we can go ahead to make it specific to this question. So ln T final, okay, divided by T initial. So you can see this is just the general equation. We have the T initial, we have the T final, we have the molar heat capacity for this question at constant pressure for this question. So that means we can substitute. But you may be wondering, why don't we have the molar entropy for the initial temperature? Well, the question does not require us to find the molar entropy for the initial temperature because we're asked to find the change in molar entropy. So we can rewrite this formula as the molar entropy at of the final temperature, okay, minus the molar entropy at the initial temperature is equal to Cp, comma m, okay, ln T final, okay, divided by T initial. So that's basically how it's done, your change in molar entropy. So change in S is equal to Cp, comma m. I'm just going to rewrite it now in terms of this question. For N2 gas, okay, ln T final divided by T initial. So the change in S is equal to Cp, comma m of N2 gas. That would be 29.125 joule per mole Kelvin. Okay, times ln T final divided by T initial. So that will be 273 kelvins divided by 298 kelvins. So that's how it's done. So having this, we have change in S, okay, is equal to 29.125 joule per mole Kelvin, okay, times, we see now that we have this information here, 273 Kelvin divided by 298 kelvins. We can cancel out the kelvins and we can do 273 divided by 298. So that will be times ln. 273 divided by 298 is 0.91611. So now we have 29.125 joule per mole Kelvin times ln 0.91611. So change in S is going to be equal negative 2.5519 joule per mole Kelvin. So when we multiply what is up here that I'm putting in a box, and you do 29.125 times ln 0.91611. Remember, the ln of anything less than 1 is going to give you a negative value, hence the reason why we have a negative here. So when you multiply both of them together, you have negative 2.5519 joule per mole Kelvin. Now, since we're dealing with a chemistry question, we cannot just say, oh, this is our final answer, right? We have to make sure that we are putting it in the correct number of sig figs, because that's how you work with chemistry problems. So in our question, we have 3 sig figs for 298 kelvins. Okay, we have 3 sig figs for 273 kelvins, we have 5 sig figs for the molar heat capacity of nitrogen at constant pressure. So we're going to pick the lowest number of significant figures because that's the rule in math or in chemistry, whatever you want to call it. So we're going to end up having our change in S to be negative 2.55 joule per mole Kelvin. So that is basically the answer to this question. So that's how it's done. If you have any questions, make sure you put it in the comment section. If you have any suggestions or concerns, make sure you also put it in the comment section. Assalamu alaikum. Welcome everyone. So today we're going to be working on the question on the screen that says, estimate the increase in the molar entropy of O2 gas when the temperature is increased at constant pressure from 298 kelvins to 348 kelvins, given that the molar heat capacity at constant pressure of O2 gas is 29.355 joule per mole Kelvin at 298 kelvins. So to solve this, the first thing you have to do is understand what you're asked to solve for. They didn't ask us to find the molar entropy of a particular value. They asked us to estimate the increase. So anytime you see that you're asked to find an increase in something, that just means that you're trying to see how much of the molar entropy has increased. So you're going to be dealing with the initial molar entropy as well as the final molar entropy. So we're dealing with a question where there's a temperature increase at constant pressure. So the pressure is constant all through, but we have an initial temperature and a final temperature. So the initial temperature for this question, for this entropy question, is 298 kelvins, and then we're told the increases to 348 kelvins. So the final temperature is 348 kelvins. So given that the molar heat capacity at constant pressure of O2 gas is 29.355 joule per mole Kelvin. So the molar heat capacity at constant pressure of O2 gas is 29.355 joule per mole Kelvin. So that is basically the question. So the first thing you have to know is anytime you're given a question for entropy, note that when you're told that this is occurring, and you're given the initial temperature as well as the final temperature as well as the molar heat capacity of a particular gas at a particular temperature, you're going to be using this formula here, which is entropy TF, okay, equals entropy T initial plus Cp comma M, okay, ln T final divided by T initial. So this is basically how you work up with a problem like this. This is basically how it's done. I apologize for the scribble. So this is basically the equation. So yeah, that's it. So you're looking for the entropy at the final temperature, and then the entropy at the initial temperature, then the molar heat capacity times the ln of the T final divided by the T initial. Since we're not asked to find for the molar entropy at the final temperature or the molar entropy at the initial temperature, and we're asked to actually find the increase, we're going to be dealing with the change in molar entropy. So to rewrite the formula, we can have the change in molar entropy for this question can be written as this. So T final minus molar entropy T initial, and then we have Cp comma M ln T final divided by T initial. So change in S is now basically Cp comma M. So molar, the molar heat capacity at constant pressure times ln T final divided by T initial. So this is actually what you're going to be working with. So of course we've reached this point. We're just going to substitute whatever we have. So we have change in S is equal to the molar heat capacity at constant pressure for O2 gas is 29.355 joule per mole Kelvin times ln T final. So that would be T final, we know that to be 348 kelvins. We know T initial to be 298 kelvins. So that's basically how it's done. Of course, we have the change in S. It's equal to 29.355 joule per mole Kelvin times ln 348 divided by 298 kelvins. Of course, because we have the same units, we can just cancel out the Kelvin. So that would be ln 348 divided by 298 is the same thing as ln 1.1678. So that's basically how it's done. You can input this information in your calculator. 29.355 times ln 1.1678 will give you the change in S to be 4.5536 joule per mole Kelvin. Now, I wanted to mention that we've gotten our answer to be correct, thankfully, but we have to go back because we're dealing with chemistry. We have to see the lowest number of sig figs that we're given in order for us to um pick this final answer. So we have three sig figs for 398. 348 also has three sig figs. Here it has five sig figs. So we're going to actually approximate our answer to three sig figs. So having that sig figs, we have our change in S to be plus 4.55 joule per mole Kelvin. And I wanted to mention this. It was very important to say anytime you're dealing with entropy question, make sure you always put a plus or a minus because it's very, very important in entropy. It's not like the previous physical chemistry problems that we've had where a positive value, we can just ignore the plus. There are so many change in entropy and molar entropy questions that can take the negative sign. So just make sure you put that into consideration and just add your plus, even though, of course, the positive can be omitted. But just for this particular topic in entropy, try to add your plus as well as minus so that you can easily differentiate and be easy for your teacher to mark. If you're a student who's trying to succeed in all your STEM related courses, I tutor students in your STEM related classes how to succeed and how to be the best version of themselves in your academic career. So if you would like to book a session, you can email me at shohabitutoring@gmail.com. I wish you guys all the very best. If you have any questions, put in the comment section. If you have any suggestions or concerns, also put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says the molar entropy of a sample of neon at 298 Kelvin is 146.22 joule per mole Kelvin. The sample is heated at constant volume to 500 Kelvin. Assuming that the molar constant volume heat capacity of neon is 3 over 2 R, calculate the molar entropy of the sample at 500 kelvins. So the first thing you have to do whenever you have a question like this is to write out the parameters. We're told that molar entropy of a sample of neon at 298 Kelvin is this. So the molar entropy at 298 Kelvin is 146.22 joule per mole Kelvin. The sample is heated at constant volume. So this is a constant volume process. Okay, so the change in V is equal to 0, meaning throughout the entire process, the volume is going to be the same. And we also know that they said that the sample is heated. So it's an increase in temperature. So it's increased to 500 Kelvin. Assuming that the molar constant volume heat capacity of neon, or assuming the molar heat capacity, a constant volume of neon is 3 over 2R. So that would be CV, comma M is 3 over 2R, which is the same thing as 3 times 8.3145, okay, joule per mole Kelvin divided by 2. Okay, we're now asked to calculate the molar entropy of the sample at 500 Kelvin. So this is actually what we're looking for. What I'm about to box right here, that I'm currently boxing, is what we're looking for. And we already know that we have an initial temperature, okay, of 298 kelvins and a final temperature of 500 kelvins. What we're actually supposed to be looking for is the molar entropy of the sample at 500 kelvins. So to continue our work with the CVM, we have to remember that CVM is just 3 over 2 times 8.3145. When we put this information in a calculator, we end up getting 12.4718 joule per mole Kelvin. When we have this information, our work is still not done. We just have to basically note that when you have a question like this, we have a formula that we use. The formula that we use is simply this one right here, which I'm writing. So the molar entropy at final, or the molar entropy at the final temperature, is equal to the molar entropy at the initial temperature, okay, plus the molar heat capacity at constant volume. If this is a question where we have constant pressure, is going to be Cp, comma m. But since it's a constant volume question, we have Cv, comma n. So you have ln times ln, the T final divided by the T initial. So that's the case here. Now we just have to simply substitute. We have to simply substitute. So we have S 500, okay, Kelvin, which is what we're looking for, is equal to the molar entropy at the T initial. So the initial temperature is 298 Kelvin, and the molar entropy at that particular point is what we have here, 146. So that's basically 146.22 joule per mole Kelvin. So all of that plus CV, comma M, so that would be 12.4718 joule per mole Kelvin. ln, so times, okay, ln T final divided by T initial. So T final, that will be 500 kelvins divided by 298 kelvins. So that's basically how it's done. You cancel Kelvin here, you cancel Kelvin here, and then we just continue our work. So we have S500 or molar heat. You can honestly, you can write SM, you can write S. Just make sure you understand that what that SM or S signifies is the molar entropy. So you have this 500 is just going to simply be this 146.22 joule per mole Kelvin, okay, plus 12.4718 joule per mole Kelvin times, so this information here, times ln 500 divided by 298 is just simply 1.67785. So there's that. And yeah, times that. So what we end up with is just basically SM 500 Kelvins, just 146.22 joule per mole Kelvin plus 12.4718 joule per mole Kelvin, okay, times ln 1.67785. When you input this information, this second part of the information after the plus sign, in the calculator, you get that to be 6.4543 joule per mole Kelvin. So when you add them up, the molar entropy at 500 Kelvin, you get 146.22 plus 6.4543. When you add them up, you end up with 152.6743 joule per mole Kelvin. Now, when we go back to the beginning of our question to be able to know what we're working on, sorry. So when we go back to the beginning of our question, we're going to see that the molar entropy at 298 Kelvin given to us was 146.22. This was in two decimal places. So we're just going to simply put our answer in two decimal places. So what we end up with is molar heat capacity, sorry, the molar entropy at 500 Kelvin just is 152.67 joule per mole Kelvin. And I also wanted to mention that it's possible that you could also write this in 3 sig figs because we have 298 Kelvin here in 3 sig figs. In case your professor asks you to solve this in 3 sig figs, what you end up with is just simply the molar entropy at 500 Kelvin is 153 joule per mole Kelvin. So this one is in two decimal places. This one is in three significant figures. If you have any questions, please put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the molar entropy of a constant volume sample of argon at 250 Kelvin. Given that it is 154.84 at 298 Kelvin, the molar constant volume heat capacity of argon is 3 over 2R. So this information is easy, even though like the question sounds like a mouthful. The first thing you have to do is, of course, write out your parameters. We're told to calculate the molar entropy of a constant volume sample of argon at 250 Kelvin. So really what we're looking for is this. So we're looking for the molar entropy, which is SM, or you can just say S, of a constant volume sample of argon at 250 Kelvin. So this is what we're looking for. Given that it is, meaning the molar entropy is 154.84 joule per mole Kelvin at 298 Kelvin. So the molar entropy at 298 Kelvin would be 154.84 joule per mole Kelvin. The molar constant volume heat capacity of argon is 3 over 2R. So that would be CV, comma M, because it's a constant volume process. That's just going to be 3 over 2R, which is the same thing as CV, comma M, equals to 3 over 2 times 8.3145 joule per mole Kelvin. So that's basically how it's done. 3 over 2 times 8.3145 is the same thing as 12.4718 joule per mole Kelvin. So now we have like this parameters written down. Now I wanted to explain something to you guys. The formula to solve a question like this, the general formula is the molar entropy at the final temperature is equal to the molar entropy at the initial temperature plus the heat capacity CVM ln T final divided by T initial, where CV comma M is because it's a constant volume process. It is if it's a situation where you're dealing with a constant pressure process, you're gonna have CP comma M. So just put that in mind that you can have this question and you're actually going to be dealing with a CP comma M because of that will be a constant pressure problem. But here we have a CV comma M. So just know that like the formula can be used either way. Now, when I quickly mention something to you, we already have oops, sorry. We already have um this one here. We already have this here. We have this. We have CV comma M. But we have to determine what is the initial temperature and what is the final temperature. You can see in this question that we're told to calculate the molar entropy of a constant volume sample of argon at 250 kelvins, given that it is 154.84 at 298 Kelvin. What this is telling you is that given that it is this, because of how the grammar is worded, we know that the initial temperature is going to be 298 Kelvin. Then there's going to be a decrease in temperature to 250 Kelvin because when they said given that it is 154.84 at 298 Kelvin, that is indirectly telling us that T initial is actually 298 Kelvin. So we can write that here. T initial is going to be 298 Kelvin. And then the temperature that we're actually giving later on is going to be the final temperature, which is 250 Kelvin. And we're supposed to calculate the answer for that. So, anyways, that's just basically how it's done. So, we're now basically going to substitute, right? So, the molar entropy at the final temperature, that's going to be 250 Kelvin. So, that's what we're looking for, is equal to the molar entropy for the initial temperature, that's 298 Kelvin, okay, plus, well, first of all, doing the first substitution, plus CV comma M, so that's just going to be 12.4718, okay, joule per mole Kelvin, times ln T final, okay, divided by T initial. So T final, that's simply 250 divided by 298. So 250 kelvins divided by 298 kelvins. So that's basically how it's done. We can, of course, rewrite this by substituting the molar entropy at 298 Kelvin. We're going to rewrite this formula. So SM of 250 that we're looking for, Kelvin, is equal to the molar entropy at 298 Kelvin. We have that to be 154.84 joule per mole Kelvin. So 154.84 joule per mole Kelvin plus 12.4718 joule per mole Kelvin times ln 250. Let's do it here. 250 Kelvin divided by 298 Kelvin. We cancel out the kelvins. 250 divided by 298 is the same thing as 0.83893. So that's basically how it's done. So of course we have SM for 250 Kelvin, okay, is equal to 154.84 joule per mole Kelvin plus, now we're going to just work with this information here, plus 12.4718 joule per mole Kelvin times ln 0.83893 is just simply negative 2.1904 joules mole, sorry, negative 2.1904 joule per mole Kelvin. So that's it. So 154.84 joule per mole Kelvin minus 2.1904 joule per mole Kelvin is just simply going to give you 152.6496 joule per mole Kelvin. Now, if we go back to our question, we see that the molar entropy for the initial temperature was given to us in 2 decimal places. So we're going to put that into account and we're going to put our answer, our final answer, in 2 decimal places. So what our molar entropy or at 250 Kelvin is actually going to be 152.65 joule per mole Kelvin. And it's also possible that you'll be asked, this is in 2 decimal places. It's also possible that you'll be asked to put this answer in 3 sig figs. That's how it usually is in chemistry, or just because we have 250 kelvins here, we have 298 Kelvin here, that's 3 sig figs. You You can also write this in 3 sig figs. And in 3 sig figs, molar entropy at 250 Kelvin is actually going to be 153 joule per mole Kelvin. So it can be either of the two. So if you have any questions, make sure you put in the comment section. If you have any concerns or suggestions, also put in the comment section. Please make sure you give this video a like and make sure you subscribe if this has been very, very beneficial for you. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, use Troughton's rule to predict the enthalpy of vaporization of benzene from its normal boiling point, comma, 80.10 degrees. So they're trying to tell us that the boiling point of this particular question is the boiling point of benzene in this particular question is 80.10 Celsius. So yeah, 80.10 Celsius. So in order for us to go, of course, from 80.10 degrees Celsius to Kelvin, we just have to add it. So that would be 273.15 plus 80.10 degrees Celsius. So you just add them up, you end up with 353 point, yeah, 353.25 kelvins. So this temperature, and whenever you're dealing with Troughton's rule, is just going to be TB, so the boiling point temperature. So that is it. Now to write out our second parameter, we're not giving a second parameter, but in order for you to know what to do next, you have to know the formula for Troughton's rule. Troughton's rule is just basically the change in vaporization enthalpy, or the change in standard enthalpy of vaporization, okay, is equal to the boiling point times, or the boiling point temperature times the change in standard entropy of vaporization. So that's going to be this right here. So this is basically what it is. And we're asked in our question to find the enthalpy of vaporization of benzene. So what we're actually looking for right here is this one that I'm writing. So this is it, the change in enthalpy of vaporization, or standard enthalpy of vaporization. So this is what we're looking for. We're already given this information here. But of course, we know anytime we're given one unknown and you have 3 different parameters, you have to make sure the 2 are known in order for you to solve for the third unknown. Well, we also know that since we're dealing with chemistry, we can always go to the resource section of our physical chemistry textbook to find the change in entropy of vaporization for the particular molecule we're dealing with, and we're dealing with benzene. And when I went to check it, I ended up finding the change in entropy of vaporization for benzene is actually 87.2 joule per mole Kelvin. So that's just basically how it's done. So of course you have 2 parameters, so you can just simply substitute. So you have the change in enthalpy of vaporization is going to equal 353.25 kelvins, okay, times the change in entropy of vaporization would be 87.2 joule per mole Kelvin. So you cancel out kelvins. So the change in enthalpy of vaporization is now going to be 353.25 times 87.2 joule per Kelvin. So that's going to actually give you 30,803.4 kilojoule, 80.4 joule per mole. So joule per mole. So you may be looking at this question, and many times whenever you're dealing with enthalpy, you're always getting the answer either in joule per mole or kilojoules per mole, but majority of the time it's in kilojoules per mole. And if you look at this question, you can see how large the value is. So what I'm going to do now is to go from joule per mole to kilojoule per mole. But before we do that, let us remember that we're going to be putting our answer in a number of significant figures that of the question that we're given. So when we see the question, we see that our normal boiling point is in 3 sig figs. Our change in entropy of vaporization for benzene is also in 3 sig figs. So we have to make sure our work is in 3 sig figs. So what that would mean is the change in enthalpy of vaporization is now going to be 30.8. Then since we're dealing with kilojoule, that's going to be 30.8 kilojoule per mole. And of course, how you do this is when you're trying to go from joules to kilojoules, okay, you're just going to divide, right, by 1000. So that's basically what I did here. I just divided by 1,000, 30,803.4. When you divide it by 1,000, you just have 30.8034. And of course, since we're doing it in three sig figs, we end up with 30.8 kilojoule per mole. So this is basically the answer to this question. If you have any questions, please put it in the comment section. I'm going to try my best to answer them. If you have any concerns or suggestions, please put it in the comment section. If you're Salam and welcome everyone. So today we're going to be working on the question on the screen that says use Troughton's rule to predict the enthalpy of vaporization of cyclohexane from its normal boiling point 80.7 degrees Celsius. So of course we know that we're dealing with Troughton's rule, and Troughton's rule is a rule in physical chemistry that has the formula change, okay, in enthalpy of vaporization, okay, or change in standard enthalpy of vaporization is equal to the boiling point temperature, okay, times the change in entropy of vaporization. So, or change in standard entropy of vaporization. So this is basically what we're dealing with. We're told the boiling point for this question is 80.7 degrees Celsius. So TB is actually 80.7 degrees Celsius. The next thing you have to do, of course, anytime you're given temperature questions like this, is to go from degrees Celsius to Kelvin. So TB ends up being 80.7 degrees Celsius plus 273.15 kelvins. So I'm doing the calculation on the side. We know that to be TB, okay, 80.7 plus 273.15 is going to give you 353.85 kelvins. So this is basically how it's done. So let me rewrite that because it's kind of smudged. So TB is 353.85 kelvins. So now you'll be wondering, okay, we're told to find the enthalpy of vaporization. So we're supposed to find this one right here, right? But we only have the boiling point temperature. We don't have this one right here. But as any chemistry student would know, whenever you're given a physical chemistry question, you should also have the information you should also be used to checking for values in the resource section of your textbook. So in the resource section of my physical chemistry textbook, I see that the value of the change in change in entropy of vaporization is actually 85.1 joule per mole Kelvin. So that is it. So now we have the boiling point temperature, and we have, of course, the change in entropy of vaporization. So we can just substitute in this equation. So having this equation, we have, or rewriting this equation, we have change in enthalpy of vaporization is going to equal, okay, just rewriting the formula and then substituting. Is what I'm trying to do right here. So change in enthalpy of vaporization is equal to 353.85 kelvins times, so that's the temperature, times change in entropy of vaporization, which is 85.1 joule per mole Kelvin. So divide Kelvin. So we have the change in enthalpy of vaporization is equal to this information right here times this information right here. When we put that in the calculator, we get 30,112.635 joule per mole. Okay, so that's basically how it's done. Now let's not forget that in enthalpy in enthalpy or change in enthalpy that we've been given thus far, a lot of our questions or answers or the values have been given to us in kilojoule per mole. As you can see in this question is much greater than the change in entropy. So we can go from joules to kilojoule per mole. So all we have to do is just divide this information by 1,000, because when you go from joules to kilojoules, you divide by 1,000. So the change in enthalpy of vaporization can be rewritten as 30, okay, 0.11264 joule per mole. So this is basically, kilojoule per mole. So this is basically the answer. But our work is not done. Because we're dealing with a question in chemistry, we have to look for the sig figs so that we can put in the proper answer in the proper sig figs. We see that we're giving the normal boiling point to be 80.7 degrees Celsius. So that means our answer will have to be put in 3 sig figs because 80.7 degrees Celsius is in 3 sig figs, as well as change in entropy of vaporization is also in 3 sig figs. So we can put our answer in 3 sig figs. So we end up having the change in enthalpy of vaporization for this particular question to be 30.1 kilojoule per mole. So this is answer to this question. If you have any questions, please put in the comment section. If you have any concerns, also put in the comment section. Salam and welcome everyone. So today we're asked to solve the question on the screen that says, calculate the standard reaction entropy at 298 kelvins when 1 mole of nitrogen gas is formed from its elements in your reference states. So the first thing you have to note is that you're asked to find or calculate the standard reaction entropy at 298 Kelvin when 1 mole of nitrogen gas is formed from its elements. So 1 mole of nitrogen gas, so NH3, so not nitrogen, I apologize. 1 mole of NH3 gas, which is simply ammonia, is formed from its elements in your reference states. So we see that ammonia gas, NH3, is comprised of 2 elements, and those 2 elements in your reference state is just simply nitrogen gas, okay, plus hydrogen gas. That reaction is what is going to give you ammonia gas, which is what we're asked to solve. So this equation is where we're supposed to, this equation is what we're supposed to calculate the standard reaction entropy of. Now, I wanted to quickly mention something to you. This equation is not balanced, and we have to balance it in order for us to start solving for the standard reaction entropy. So the first thing you have to understand is this. Whenever you're given a question like this, it's best for you to balance the chemical equation in such a way that you only have 1 molecule of NH3. So what this is telling you is this: you're going to write, or we're going to balance this chemical equation in such a way that we only have 1 molecule of NH3 gas, because this is the most basic form that we can have the NH3 gas, so that it's easy for us if we need to manipulate any of our work in future. So 1 molecule of ammonia gas is the same thing as having 1 one atom of nitrogen as well as 3 atoms of hydrogen. And in this particular situation, we have 2 nitrogens and 2 hydrogens. So we're just gonna basically like manipulate it with our understanding of how to properly balance chemical equation. So we need to have 1 atom of nitrogen on the left hand side as well. So what you just do is just turn this into half, because half of 2 is 1. So now you've automatically balanced the nitrogen to also have 1 nitrogen on the left hand side. Now we're also going to do the same thing for hydrogen. Here we have 3 hydrogens. Here we have 3 hydrogens. Here we have 2. Well, to go from 3 to 2, you just have to have 3 over 2 here. So 3 over 2 times 2 is just basically 3. So that would be 3 hydrogens. So as you can see, you have successfully balanced. And that way to think about it is also in terms of decimal. 0.5 times 2 is 1, and then 1.5 times 2 is 3. So if you notice, we've balanced the chemical equation. So I'm just going to rewrite this balanced chemical equation as half N2 gas, okay, plus 3 over 2 H2 gas, okay. This is the balanced chemical equation plus NH3 gas. So this is what we're going to be using. Now, the next thing you have to note is this, because the work just started, is when you're asked to find the standard reaction entropy of anything, you have to remember the formula you're supposed to be using. The standard reaction entropy formula is simply the summation, okay, of the molar entropy of the products, okay, minus the summation of the molar entropy of the reactants. So what this looks like is that you are going to organize this chemical equation in terms of this formula. So we're going to have this: the molar entropy of the product, we know our product to be NH3 gas, okay? Okay, minus the molar entropy, of our reactant. The first reactant is N2, so the molar entropy of half N2 gas, because we're applying it to this particular equation, plus the molar entropy of the second reactant, which is just 3 over 2 H2 gas. So that is it. So the next thing you're going to do now is that you're going to rearrange this in such a way that you make our work neater and easier to understand. So what this simply means is that we're going to bring out the coefficient that is not 1. Now, before we do that, I want to quickly say something. Remember how I have this V here and this V here. What this V is telling you is that this is the coefficient value for the products, or for each individual product. Okay, so this is a coefficient value for each individual product, and here you have the coefficient value for each individual reactant. So that's what this V here. And of course, you see that the V here for the reactant is 1. So we're not going to pay attention because the coefficient of 1 is just 1. It's not like an interesting situation. As well as the coefficient here is half for the nitrogen and then 3/2 for the hydrogen. So putting that in mind, I'm going to reorganize our work. So we're going to have molar entropy. So just bear with me. If you've been watching my videos, you know exactly what I'm about to do. Okay, the molar entropy minus half, okay, times the molar entropy of nitrogen gas, okay, because that's how it's meant to be done, plus 3/2 times the molar entropy of hydrogen gas. So this is how the work is done. Now, the next thing you do after all of this is for you to simply substitute. And for those of you who don't know, all what I've been doing on my physical chemistry playlist is simply questions that are from the physical chemistry Atkins 11th edition textbook. And in this particular question, we use the resource section of our textbook, meaning the back of our textbook, to have the molar entropies of each one of the molecules. We do not Google it. We're not giving it in the question, but we know that we're going to use the resource section of our textbook to answer this question. So I'm just going to be substituting values from the resource section of the textbook. Anyways, moving forward, we have the molar entropy of nitrogen gas to be 192.45 joule per mole Kelvin, okay, minus 1/2 times the molar entropy of N2 gas is just 191.61 joule per mole Kelvin. Okay, that's 1. So this information here for now. And then you have the plus, because of course we're dealing with summation, plus 3/2, okay, times the molar entropy of H2 gas is just 130.684 joule per mole Kelvin. So that's it. So you have 192.45. So the molar entropy of, the entropy or the change in entropy of reaction is just simply 192.45, okay, joule per mole Kelvin. Joule per mole Kelvin, okay, minus half of 191.61 joule per mole Kelvin is simply 95.805 joule per mole Kelvin plus 3/2, or 1.5 times 130.684, or 3/2 times 130.684 joule per mole Kelvin. That would be plus 196.026 joule per mole Kelvin. So that's basically how it's done. So we have 192.45 joule per mole Kelvin minus 95.805 joule per mole Kelvin plus 196.026 joule per mole Kelvin. So that would be minus 291, okay, 0.831 joule per mole Kelvin. So the change in standard entropy of reaction will be negative 99.381 joule per mole Kelvin. Now, I want to quickly mention something to you. Anytime you're dealing with physical chemistry question or just a chemistry question in general, you have to look at the proper number of sig figs as well as decimal places you're supposed to put your answer in. In this particular question, we have our values that we're using to be in 2 decimal places here, 2 decimal places here, 3 decimal places. In chemistry, we pick the value with the lowest number of decimal places. So we're going to have to put our final answer in 2 decimal places. So what we have is going to be negative 99.38 joule per mole Kelvin. Now, you would think the work is already done, but it's not. Let's go back to our question. We're told calculate the standard reaction entropy at 298 Kelvin when 1 mole of NH3, so of ammonia gas, is formed. We're told 1 mole of NH3 is formed from its element. So what this means is that we're going to multiply whatever our value is times the number of moles to be able to get our actual answer. So our answer here would just simply, the standard reaction entropy would just simply be negative 99.38, okay, joule per mole Kelvin times 1 mole. So cancel this out. Just basically what we calculated had mole, and what we ended up getting as our formula answer when we multiplied the answer by 1 mole is going to be in just joule per Kelvin. So that's just the only difference. So basically what our answer is going to be now will be negative, okay, 99.38 joule per Kelvin. And this is basically the answer that we're asked to solve. If we're not told when 1 mole of NH2 is formed, and we're just so told when NH2 is formed from its element, we're not going to do the last process where we multiplied what we calculated for the standard reaction entropy by number of moles. We're just going to leave it as negative 99.38 joule per mole Kelvin. But since we're told, particularly when 1 mole, we have to multiply it, and then we have negative 99.38 joule per Kelvin. Hopefully, this has been easy for you guys to understand. If you have any questions, suggestions, or concerns, make sure you email me at yourhabitutoring@gmail.com, or just simply put it in the comment section. Salam and welcome, everyone. So today we're going to be working on the question on the screen that says, use the data from the resource section to calculate the standard reactant entropy at 298 Kelvin of the following reactions. We have 3 different reactions here, and we're asked to use the data from the resource section to calculate the standard reactant entropy. Now, the first thing you have to note is the resource section of the textbook we're going to be using, or we're using, is the Atkins Physical Chemistry 11th edition. So I have gone to my textbook and written the resource section for every single value, entropy value for every single molecule that we're going to be calculating in those series of reactions. So make sure you um write down this question, as well as pause this video and write out all of the values from the resource section that are currently on the screen. So now that you've written all of it, we're going to start with the questions. So the first thing you have to know is, when you're asked to find the standard reactant entropy, is for you to know that the standard reactant entropy is equal to the formula, the summation of the entropy of the different products, okay, for each reaction, minus the summation of the entropy values for the reactants as well. So basically, this is just the formula, and it's not going to be like properly explained until we start solving questions. And I hope like you guys have paused the video, because I'm not going to be going back and forth on the first page to get the values, to get the reactions, just because I have my notes, and because you can just simply pause, rewind this video, pause to where you need all of the information, and then you can continue. So the first reaction is 2CH3, okay, CHO gas plus O2 gas, okay, would give you 2CH3 COOH liquid. So that's it. That's the first reaction. So the way you're going to do this is that you're going to arrange this based on this formula. So the standard reaction entropy becomes the product. So you have the molar volume, sorry, not the molar volume, the molar entropy for the product in this question is just 2CH3, okay, C2COOH liquid, okay, minus the molar entropy for the reactant. The first reactant, which is just 2CH3 CHO gas, okay, plus molar volume, that of O2 gas right here. So that's basically how it's done. Now, the next thing you have to simply do is for you to rearrange or reorganize this particular question. So you have this right here. The standard entropy of reaction would just simply be 2 times the molar volume of the molecule. So we're not just going to be finding the molar volume of 2CH3, because that does not exist in the resource section of our text. That does not even exist in chemistry. This is just telling us how many of 2CH3COOH or how many of 2CH3CHO. We just have to bring out the coefficient, or the number of the amount, times the molar volume of the actual molecule or compound. So that's how it's done. So now we're just going to say CH3COOH liquid. Okay, minus, do the same thing here, 2 times the molar entropy for this one. So that would be CH3 CHO gas, okay, plus the molar volume of O2 gas. The standard entropy of reaction becomes 2, okay, times 159, which is the value, 159.8 joule per mole Kelvin, okay, minus 2 times the first product, the molar entropy of CH3CHO, we know that to be 160.2 joule per mole Kelvin, okay, plus the second product, the molar entropy is just 205.138 joule per mole Kelvin. So the molar entropy or reactant entropy simply 2 times 158.9, 159.8 actually, sorry, is just simply 319.6 joule per mole Kelvin minus 2 times 160.2 is just 320.4 joule per mole Kelvin plus 205.138 joule per mole Kelvin. So that's how it's done. So the standard entropy of reaction becomes 319.6 joule per mole Kelvin minus 320.4 plus 205.138 will simply be 525.538 joule per mole Kelvin. So you have the standard entropy of reaction simply is 319.6 minus 525.538. That will be negative 205.938 joule per mole Kelvin. Now, this is the answer to our question. But one thing you have to remember is that since we're dealing with a chemistry question, and we have a lot of additions in this question, the proper thing we're supposed to do is to make sure that we have the proper number of decimal places in our final answer. So we have to look for we have to go back to our question and see what has the lowest number of decimal places. We have one decimal place here, we have one decimal place here, we have three decimal places here. So the lowest number of decimal places is one. So we're just going to make sure we approximate this, our answer, to one decimal place. So that will be negative 205.9 joule per mole Kelvin. So this is basically the answer to our question. So that's basically how you do this. The second question is the second reaction. Of course, the second reaction is simply AgCl, okay, 2AgCl solid, okay, plus bromine liquid, okay, will give you 2AgBr solid plus chlorine gas. That's basically how it is. So now we're going to go back to our knowledge of chemistry from the beginning. So the standard reaction entropy, or the change in standard reactant entropy, is just simply going to be the summation of the values for the molar entropy of the product, okay, minus the summation of the values of the molar entropy of the reactant. So we have the products, we have the reactant. So we have this here. So the molar entropy for the product is just simply going to be added minus the added information for the molar entropy of reactant. That's simply what we're going to do here. So what we end up with, we're going to start with the first product. So we have molar entropy of 2AgBr, okay, solid, plus the molar entropy of the second product, chlorine gas, minus the molar entropy of the first reactant, 2AgCl, okay, solid, plus the molar entropy of the second reactant, bromine liquid. And note that I'm saying gas, solid, liquid. I'm saying this purposely because it's possible for you to be given a question where you can have say for example, if you had a question H2O, you can have H2O gas, you can have H2O liquid, you can have H2O solid. So it's very important that you stick to the phase at which the reaction is occurring, because that's the only way you can properly solve for the answer. It's very important to know that these values, a particular molecule can have multiple phases, and because it has multiple phases, it would have different values for the different phases. So that's basically how it's done. So of course now we just simply reorganize again for the second time. So you have 2 times the molar entropy, just like we did the first, of AgBr solid, plus the molar entropy of chlorine gas, minus 2 times the molar entropy of AgCl solid, okay, plus molar entropy of bromine liquid. Okay, so now we can just simply substitute. So we have 2 times the molar entropy of the AgBr, based on the research section of our textbook that I had written earlier, is just 107.1 joule per mole Kelvin, okay, plus the molar entropy of Cl2 liquid, or Cl2 gas, to 23.07 joule per mole Kelvin. Okay, minus, oh, I must say plus, minus 2, okay, times the 96.2 joule per mole Kelvin, which is simply the molar entropy of HCl plus just the molar entropy of Br2 liquid. So that will be plus 152.23 joule per mole Kelvin. That's basically how it's done. So the change in standard entropy becomes 2 times 107.1 is just simply 214.2 joule per mole Kelvin, okay, plus 223.07 joule per mole Kelvin minus 2 times 96.2 is just simply 192.4 joule per mole Kelvin. I'm also going to be expanding it and removing the bracket for the second one as well. So we're just going to have another minus 152.23 joule per mole Kelvin. So when you add all of this information up in your calculator, so all the information 214.2 plus 223.07 minus 192.4 minus 152.23. When you add this information in your calculator, you end up getting plus 92.64 joule per mole Kelvin as the answer. But then again, we are scientists and we want to make sure we have in the proper number of decimal places. So we go back to our question and see the values we have before we start the solution. We have this value here to be in one decimal place, two decimal places, one decimal place, two decimal places. We're going to pick the one with the lowest number of decimal places. So our answer ends up actually being the change in standard entropy of reaction becomes positive 92.6 joule per mole Kelvin. So the third equation, Hg, liquid, plus Cl2, gas, okay, will give us HgCl2, solid. So the change in reactant entropy of this is going to be what? It's going to be basically what we've been doing so far. Remember what I said, the change in reactant entropy, the change in standard entropy of reaction is just simply the summation of the molar entropies of the products, okay, minus the summation of the molar entropies of the reactants. So basically what we've been learning so far. So we're just going to apply that knowledge to this question as well. So, and again, you can pause this part of the video and just try it based on how I taught you number 1 and number 2. So yeah, you can try it yourself and see if you get the same answer I get. Anyways, continuing going forward, we have the products first. So the molar entropy of the products HgCl2 solid, okay, minus the molar entropy of the reactant. So that would be Hg liquid, okay, plus molar entropy or this, yeah, the standard entropy of the second reactant, which we have to be chlorine gas. So that would be Cl2 gas. Now, all we have to do is simply substitute because, as you can see, the coefficient that we have in all of this question is 1. None of them is greater than 1. So we don't have to like organize it further by bringing out any coefficient. We can just simply substitute. So when we simply substitute, what we have is we're going to focus on the product first, which is 146.0 joule per mole Kelvin, okay, minus 76.02 joule per mole Kelvin plus 223.07 joule per mole Kelvin. So, of course, writing it again, the change in standard entropy is just going to be 146.0 joule per mole Kelvin minus 76.02 joule per mole Kelvin minus 223.07 joule per mole Kelvin. So the change in standard entropy of reaction would just be putting all of this information in the calculator. And when I did that, I got negative 153.09 joule per mole Kelvin. So that's how this is done. Of course, we already know, again, because we're dealing with a chemistry question, this is not our answer. We have to go back to see the lowest number of decimal places and use that. We have 1 decimal place here, 2 decimal places here, 2 decimal places here. So 1 decimal place would mean our answer is going to stop here. So The actual answer is approximately negative 153.1 joule per mole Kelvin. So this is basically the answer to this question. If you have any question, please put it in the comment section. If you have any concerns or suggestions, also put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen, which says use the data from the resource section of the textbook to determine the standard reaction entropy at 298 Kelvin of the following reaction. So I apologize. Let me quickly write to determine here. I don't know what happened. Anyways, use the data from the resource section of the textbook to determine the standard reaction entropy at 298 Kelvin of the following reactions. The first reaction and then the second reaction. I wanted to mention that the textbook I'm using is the Physical Chemistry Atkins 11th edition textbook, and the question stops at the second reaction. But because I'm going to be doing this video and I want to make sure everyone is on the same pace, for example, if you don't have the Atkins Physical Chemistry 11th edition textbook, the resource section is at the back of the textbook, and I have gone to the resource section and I've written all of the values that we're going to be using. So I would advise you, or I'll actually require you to pause this video and write all of this information down so that when we start to use these values in our calculation, you're not left confused. So basically pause this video, write all of this information down because I'm not going to be going back and forth through the pages because I actually have my own personal note. So now that you've already written that down, the first thing you have to do is whenever you're asked to determine the standard reaction entropy, the formula for determining the standard reaction entropy is just simply the summation, okay, of the molar entropy for the products, okay, minus the summation for the molar entropy of the reactants. So this is how you basically determine it. And this formula can be applied to any of the different chemical equation. So let's start with the first question. We're told that zinc solid plus Cu2 plus aqueous would give you zinc 2 plus aqueous, okay, plus Cu solid. Now, from this, we can apply what we know from what I've said. Now, the standard reaction entropy is just going to be simply the molar entropy of the products. So the first product in this reaction is Zn2 plus. So molar entropy of Zn2 plus aqueous, okay, plus the molar entropy, because of there's a summation here. So we're going to do the second one of the second product, which is just Cu solid, okay, minus the molar entropy of the first reactant, which is Zn solid, okay, plus the molar entropy of the second reactant, which is Cu2 plus aqueous. So yeah, that's basically how it's done. So now remember what I said. We are going to be using the values I'd given you. Like these values I told you guys to pause and write out is what we're going to be using. I have my book, so I'm just going to be simply substituting. So we have the value for the first one. The molar entropy for Zn2 plus is just simply negative 112.1 joule per mole Kelvin, okay, plus the molar entropy of Cu solid is just 33.150 joule per mole Kelvin, okay, minus the molar entropy for Zn sulfur will just simply be plus 41.63 joule per mole Kelvin, okay, plus the molar entropy for the second reactant, Cu2 plus, is just simply negative 99.6 joule per mole Kelvin. So that's basically it. Now we just do basic calculation. So the molar entropy of the reactant would just be negative 112.1 plus 33.150, which is just simply negative 78.95 joule per mole Kelvin, okay, minus plus 49.63, okay, plus minus 99.6 will just simply give you. So basically, I am working on just this information here that I have put that stuff in, like I've put that red symbol on. So what I'm saying is positive 41.63 minus 99.6 will just simply give us negative 57.97 joule per mole Kelvin. So you have The change in standard entropy of reaction will be negative 78.95 joule per mole Kelvin, okay, plus 57.97 joule per mole Kelvin. So when you add this information up, the change in standard reaction entropy will simply be negative 20.98 joule per mole Kelvin. So this is basically the answer to this question. Now, our work is not done because the proper thing for you to do in chemistry is to go back to your question to make sure that you've put in the proper number of sig figs or decimal places in this question, because we're dealing with a bunch of additions. We're going to be working with just decimal places. So I have to look at each one of the information we have that we use in this particular question and determine the number of decimal places that is the lowest. And we're going to put our answer in the lowest number of decimal places. So in this place, we have one decimal place, okay? We have three decimal places. We have two here and we have one. So we're going to put our answer in one decimal place. So we're going to approximate to one decimal place. So that would be the change, standard entropy of reaction would be negative 21.0 joule per mole Kelvin. And this is simply the answer to our question. So yeah, if you have any questions so far, please put in the comment section. Now we're going to deal with the second reaction. The second reaction, rewriting it, is C, okay, 12H22O11 solid, okay, plus 12O2, okay, gas. Are you listening? Yep, you are. Would give us 12CO2 gas, okay, plus 11H2O liquid. This is a combustion reaction. So this is the combustion reaction of sucrose. This is actually sucrose. So yeah, I mean, we don't need that information to solve this question, but it's just a fun fact. This is sucrose. Anyways, so you have that. And remember, what did I teach you? The standard entropy of reaction is simply the summation of the molar entropy of the products, okay, minus the summation of the molar entropy of the reactants. I want to quickly mention something to you. You see this V value right here. This V value here is simply the coefficient, okay, of products, okay. I did not say it in the first one because the information was not necessary, but it's going to be very necessary in this one. While this one that I'm writing is a coefficient for reactants. You're going to see why this is important soon for reactants. So we have this formula. We're just going to start. So we're going to start with the product, right? The molar entropy of the product. We've got our first product to be 12 CO2 gas, okay, plus the molar entropy for the second product, which is 11H2O liquid, okay, minus the molar entropy for the reactant. We have the first reactant to be sucrose, so molar entropy of C12H22O11 solid. And make sure you put it all of this information in the proper phase, because the entropy, molar entropy for maybe H2O liquid will be very different from H2O gas, as well as going to be different from H2O solid. So the phase of each compound is very, very important. So that's why I keep saying solid, gas, liquid. It is for a purpose. It's very, very important because the values would differ based on the different phases. So we're going to do now the molar entropy for the second reactant, which is 12O2 gas. So that is it. So yeah, now we're going to rearrange this. So we have the molar entropy. We're going to rearrange this. We're going to say 12, which is the coefficient that I explained earlier, coefficient for products and coefficient for reactant. If the coefficient is not 1, you're going to do the second step. If the coefficient is 1, then we don't need to do the second step. That's why the first question we did on this video, we only arranged it once. We didn't do a second arrangement because the coefficient for every single molecule in this reaction is 1. Here we have coefficient of more than 1. So we're going to bring out the first coefficient. So that'll be 12 times the molar entropy of CO2 gas, okay, plus 11 times the molar entropy of the second product, so H2O liquid, minus, we're going to do the same thing here. This one, the coefficient is 1, so we're just going to rewrite this. So the molar entropy of C12H22O11 solid, okay, that's what we're doing here, okay, plus the 12, okay, times the molar entropy for the second reactant, which is just not 12. We brought out the 12 already. So that would be just the second reactant is just O2. So that would be O2 gas. Yeah, that's how it's done. So now we just simply substitute based on the information I told you guys at the beginning to pause. So the information from the resource section of our textbook. So we have 12, okay, times 213.74 joule per mole Kelvin, okay, plus 11 times molar entropy of H2O, that would be 69.91 joule per mole Kelvin, okay, minus molar entropy of C12H22O11. So that's just going to be 360.2 joule per mole Kelvin plus 12 times 205.138 joule per mole Kelvin. So the molar entropy, sorry, the entropy of the standard entropy of reaction would be 12 times 213.74 is just simply 2564.88 joule per mole Kelvin, okay, plus 11 times 69.91, that's just going to be 769.01 joule per mole Kelvin. So this one's together, of course, then we got the minus. So that would be minus 360.2 joule per mole Kelvin plus 12 times 205.138 is just 2461.656 joule per mole Kelvin. So you're going to add up this information here as well as add up this information here. And we're going to input that information in our calculator. So the change in standard entropy of reaction becomes adding the first part, 2564.88 plus 769.01. That's just going to give you 3333.89 joule per mole Kelvin minus 360.2 plus 2461.656 joule per mole Kelvin. So that would be minus 2821.856 joule per mole Kelvin. The change in standard entropy of reaction will be 512.034 joule per mole Kelvin. So that is basically the answer to this question. Now, I wanted to also tell you this, right? When we're dealing with chemistry, remember we have to look at the proper number of decimal places since we have a lot of additions in this question. So we have the values we have. We have the molar entropy of reaction. We've got this in 2 decimal places, 1 decimal place, and then 3 decimal places. So we're going to put our answer in 1 decimal place. So our answer ends up becoming the change in standard entropy of reaction is 512.0 joule per mole Kelvin. And this is basically the answer to this question. If you have any questions, please put in the comment section. If you have any suggestions and concerns, also put in the comment section. If you're a student who is striving to succeed in all your STEM related courses and you would like a tutor, I'm a tutor for STEM related courses for students in middle school, high school, and college. And I do online tutoring for individuals as well as group tutoring. So if you need help, just make sure you don't forget to email me at shahabitutoring@gmail.com. And if you're also struggling and you're in need of any form of mentoring related to academia while you're trying to navigate your academic life, make sure you email me at shahabitutoring@gmail.com. I also help students who are struggling to navigate the academic path to succeed. So I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.